Bismillahirrahmanirrahim. I'm Amal Suhail and my roll number is 21TE04. Today I'm going to implement Lab 4 of Digital Signal Processing, which is about linear time invariant systems. The objective of this lab is to analyze discrete time linear time invariant systems. Task A of the lab is: how would you differentiate between a signal and a system? Explain the key characteristics of each and provide examples to illustrate their roles in the context of signal processing. So basically, what is a signal? A signal carries information. It is a comparison between two quantities. Signals are vectors. It is the relationship of one parameter with another parameter. Physical quantities that change with respect to some independent variable, for example, time, space, etc. When probability is less than 1, we can say that it is a signal. Signals come from sensors. There are various key characteristics of a signal, which includes amplitude, period, frequency, and domain. So what is amplitude? Amplitude is the height or intensity of the signal measured in units such as volts, amperes, or watts. Period: the amount of time it takes for the signal to complete one cycle measured in units such as seconds, milliseconds, or microseconds. Frequency is the number of cycles per second measured in units such as hertz, kilohertz, or megahertz. Domain: the mathematical representation of the signal such as time, frequency, or Laplace. There are several characteristics and examples of the signal in signal processing field, which includes audio signal, biomedical signal, radar signal, and sensor signal. So let me explain a few examples. Like in case of audio signal, it is an electrical voltage that varies with time, representing sound waves. Its role in signal processing field is that the signals are analyzed, modified, or synthesized for applications like music production, speech recognition, and noise cancellation. In biomedical field, for example, the ECG signal, it is the electrical activity of the heart over time recorded as voltage variations. Biomedical signal processing is crucial for tasks like heartbeat detection and heart rate variability measurements. Radar signal is used in radar systems that reflects of objects and provides information about their distance and velocity. Radar signal processing involves tasks like target detection, tracking, and Doppler shift analysis for applications in air traffic control and military surveillance. For sensor signal, it is a voltage or current variation from a temperature sensor in response to changes in temperature. Signals from sensors are processed to extract meaningful information, calibrate measurements, and compensate for environmental conditions. Now, let me tell you something about the system. What is a system? System basically create modified signals, and these systems generate new signals in response to input signals. So, a system is made up of individual components or elements. A system receives inputs, processes them through its internal mechanisms, and produces outputs. There are several characteristics of systems that include linearity, time invariance, causality, and stability. In case of linearity, a system can be linear or nonlinear depending on whether they satisfy the properties of superposition and scaling for any input signals. They can be time invariant or time varying depending on whether their behavior changes with time or not. They can be causal or non-causal, depending on whether their output depends only on the present and past values of the input or also on the future values. They can be stable or unstable, depending on whether their output remains bounded for any bounded input or not. The role of system in signal processing field includes various examples. So let me consider two examples, which are digital image processing systems. It includes components like image sensor, digital processor, display, etc. The interconnections are: digital processor analyzes pixels and applies algorithms. The input of the system is image signal with pixel intensity values, and the process occurs inside the systems, which carries out algorithms for tasks like edge detection, image enhancement, or compression. The output of the system is a processed image displayed on a monitor. The purpose or function is to improve or extract information from digital images. Now let me consider the second example, which is of communication system. It includes the components like transmitter, channel, receiver. The interconnections involves the transmitter encodes, channel transmits, and receiver decodes. The input of the communication system is the information signal, which includes voice signal or data signal. The system carries out the modulation, transmission, or demodulation, and the output obtained from the process or the system is a received information signal. The purpose of the function is transmit information over a communication channel. Task B is how does linear time invariant systems play a crucial role in digital signal processing, considering their mathematical simplicity, adherence to the superposition principle, and efficiency in frequency response analysis. So, LTI linear time invariant systems maintain a constant response over time, exhibiting linearity and time invariance. They adhere to the superposition principle, allowing for straightforward analysis and processing, especially in the domain of digital signal processing. Let us start with the mathematical simplicity. LTI systems are characterized by straightforward mathematical expressions typically described by linear differential or difference equations. This simplicity facilitates the analysis and modeling of system behavior, aiding the development of efficient algorithms for digital signal processing tasks. Superposition principle. The adherence to the superposition principle simplifies the handling of complex signals. This principle states that the response to a sum of individual inputs equals the sum of responses to each input separately. This linearity allows engineers to break down complex problems into more manageable components, streamlining system analysis and design. Efficient frequency response analysis. LTI systems efficiently analyze frequency responses through the Fourier transform of their impulse response. This streamlined process provides a clear understanding of the system's behavior across different frequencies. Engineers can easily assess filtering properties, resonance, and overall frequency characteristics, simplifying the design and optimization of filters in various signal processing applications. There are various applications in the field of digital signal processing which involve filtering, sampling, interpolation, and reconstruction. Applications are the uses of LTI systems in digital signal processing. Filtering involves removing or enhancing certain frequency components from a signal. Sampling is the conversion of a continuous signal to discrete signal. Interpolation involves increasing the sampling rate of a discrete signal, whereas reconstruction involves converting a discrete signal to a continuous signal. The task C of the lab is what are the common methods for signal decomposition, specifically focusing on techniques like impulse decomposition, step function analysis, even odd decomposition, and Fourier analysis. Explain how these methods contribute to breaking down signals and their applications in signal processing. Signal decomposition is the process of expressing a complex signal as a sum of simpler signals, which can be easier to analyze and manipulate. Some of the common methods for signal decomposition are impulse decomposition. It decomposes a signal into a series of impulse functions, each representing a unit amplitude at a specific time. And its application is that it is useful in analyzing system responses to individual impulses, facilitating the understanding of system behavior and response characteristics. Step function analysis. It decomposes a signal into a series of step functions representing sudden changes in amplitude. It allows the study of signal behavior during transitions and aids in understanding system dynamics, especially in control systems and circuit analysis. Even odd decomposition. It decomposes a signal into an even and odd components representing symmetric and anti-symmetric parts. Applications is it is useful in analyzing the even and odd symmetry properties of signals often applied in filter design, image processing, and modulation schemes. Fourier analysis. It decomposes a signal into a sum of sinusoidal components through the Fourier transform. Its applications are fundamental in understanding a signal's frequency content, aiding in filtering, compression, modulation, and various applications in signal processing and communication systems. Task D of the lab is what is convolution and how does it play a significant role in digital signal processing systems? Explore the fundamental concept of convolution and elaborate on its importance in various DSP applications such as filtering, signal processing, and system analysis. What is convolution? Convolution is a mathematical operation that combines two signals to produce a third signal. In the context of DSP, it has certain applications and importance, which includes filtering. Convolution is fundamental for implementing linear filters. The response of a system to an input signal is obtained through convolution with system's impulse response. This is essential in applications like audio processing, image processing, and communications. System analysis. Convolution enables the analysis of how a system responds to various inputs. It simplifies the understanding of system behavior and is crucial in characterizing and designing systems, especially in control theory and communications. Then comes signal processing. In signal processing, convolution is utilized for operations such as smoothing, differentiation, and modulation, providing versatility in manipulating signals. Correlation. Cross-correlation, a related operation, is employed in applications like pattern recognition, speech processing, and communications to identify signal similarities. Then comes image processing. Convolution plays a vital role in image processing for tasks like blurring, sharpening, and edge detection, widely used in convolutional neural networks for computer vision. Efficient algorithms. Fast convolution algorithms such as fast Fourier transform (FFT) for efficient convolution in the frequency domain are widely employed in DSP. These algorithms optimize the computational complexity, making real-time signal processing feasible. Task E of the lab is when do we correlate two signals and what are the key applications or scenarios where signal correlation is crucial in various fields such as communication systems, radar and sonar, image processing, biomedical signal processing and control systems, wireless communications and seismic signal processing. What is correlation? Correlation is a measure of similarity between two signals or how one signal is interdependent on another signal or how one signal is related to another signal. It can be used to detect the presence, location, and shape of a signal in a noisy environment or to compare the characteristics of two signals. Signal correlation is crucial in various applications. Let us start with communication systems. In wireless communication, correlating transmitted and received signals helps in symbol synchronization and channel estimation. The applications involve CDMA, code division, multiple access systems use correlation for signal demodulation and multiple access. Radar and sonar. Radar and sonar systems use correlation to detect echoes and determine target distances. The applications involved pulse compression, where correlation enhances the detection of weak echoes and improves range resolution. Then comes image processing. In image processing, signal correlation is applied for template matching, object recognition, and feature extraction. The applications involve facial recognition systems for matching facial features against stored templates. Then comes biomedical signal processing. In biomedical applications, correlation is crucial for analyzing physiological signals For example, ECG electrocardiogram signal processing involves correlating heartbeats for rhythm analysis and anomaly detection. Then comes control systems. Correlation aids in system identification and monitoring for feedback control. The applications involves analysis between reference and output signals, enhances controller tuning and system performance. Wireless communications. Correlation is employed in wireless systems for synchronization, channel estimation, and interference mitigation. The applications involve Wi-Fi and cellular systems use correlation to synchronize transmitted and received signals in multipath environments. Seismic signal processing. In seismic exploration, correlation is utilized to analyze ground vibrations and identify subsurface structures. Applications are identifying seismic events, estimates underground resource locations, and monitors geological activities. Here is the task 1 of Dsp Lab 4, which is about coding in MATLAB. The question is, make your own customized function that takes two input signals from user and show convolution sum graphically. Here is the MATLAB code. Firstly, it prompts the user to enter the first signal along with its time indices n of x. Then it again prompts the user to enter the second signal along with its time indices n of h. Then it calls the convolve function and receives the convolution result y along with its indices n of y. The figure statement generates a new figure in MATLAB. Different subplot commands are used to plot different graphs in the similar figure. The first subplot represents the input signal, and title and labels are used for the better visual representation of the graphs. The second subplot represents the impulse response h of n, whereas the third subplot represents the convolution result. Then nmax and nminimum command calculates the minimum and maximum indices for the convolution result. Then ny is equal to nminimum colon nmax creates a range of time indices n of y for the convolution result. And last statement y is equal to convx comma h represents the convolution sum using the built-in MATLAB conv function with the input signals x and h. Let us call the function. The command window asks for inputting the first signal. Let us enter a new signal which is 1 1 1. Now it asks the user to enter the specific indexes for the signal 0 1 and 2. Now entering the second signal, which is -1 -2 and 3, for example. And let us enter the specific indexes for this signal 0 1 2. Here is the graph. The first subplot represents the input signal, the second subplot represents impulse response, whereas the third represents the convolution result y of n. This code basically takes two signals and their corresponding time indices from the user, performs convolution using the convolve function, and then displays the input signals along with the convolution result graphically using subplots. The graphical representation aids in understanding the signal processing operation. Task 2 of the coding part of the lab is make your own customized function that take two input signals from user and use flip and slide method to show convolution sum step by step. The hint is use pause command to stay and see stepwise convolution results. Let us see the MATLAB code. The MATLAB code creates a function named myconv. Firstly, it prompts the user to enter the first signal x of n. Then it asks for the specific time indices for the x of n signal. Then it again prompts the user to enter the second signal, which is h of n, and also asks to enter the time indices for the specific signal. The nmin and nmax commands are used for the time indices of the convolution result. Then it creates a range of time indices n of y for the convolution results and then stores this result in the resulting index y, resulting array y. The code then uses the for loop to iterate through each time index of the result, and then it initialize and then it compute the convolution sum for the current time index using flip and slide method. After that, it create a new figure and plot the results using flip and slide method and plots the final convolution results in the graph. Let us run this code. Firstly, it asks the user to enter the first signal, which let us take an example of a simple signal, which is 1, 1, 1. Let us enter the specific indexes of this signal, 0, 1, 2. The next signal is 1, minus 2, 3. And indexes for this signal are 0, 1, 2. Let us enter. It is the first step of the convolution result. By pressing enter or by clicking anywhere in the graph, we can observe step-by-step convolution results of this code. Let us press enter and check for the second convolution result. Here we can see the stepwise result of the convolution sum. Now the new figure is generated, which shows the complete convolution sum result of the code. So this code essentially performs convolution step by step using flip and slide method, allowing the user to visualize the convolution process at each intermediate step before displaying the final result graphically. The pauses between steps are introduced to give the user time to observe the computation. Task 3 of the lab is to compute the response of the following system to the input x of n. To build a user-defined function for this example, 4 arguments will be passed to the function: input x of n, information about its origin, impulse response h of n, and information about its origin. Let us observe the code. This MATLAB code defines a function named myconv2 to compute the convolution of two sequences x and h along with their corresponding time indices nx and nh. The first statement represents the calculation of the starting and ending indices of the resulting convolution sequence by adding the first and last elements of the time indices of sequences x and h respectively. The next line generates the indices for the convolution result, and the resulting convolution sequence y and its corresponding time indexes ny are returned as outputs. In the calling section, x and h are defined sequences while n of x and n of h are their respective time indices. myconv2 is called with x, nx, h, and nh producing the convolution result y and its corresponding time indices n of y. The convolution result is plotted using stem width green color and a line width of 1.5. The title of the plot is convolution result y of n. The x-axis is labeled as n, representing the time index, and y-axis is labeled as amplitude, representing the magnitude of the convolution result. Let us run the code and observe the output. Here is the result of the convolution of the two signals x of n and h of n according to their respective time indices. Task 4 is the last task of the Dsp Lab 4, and it is: we have the impulse response of a system as x of n is equal to 3 to 1 minus 2 1 0 minus 4 0 3. For x of n is equal to 1 minus 2 3 minus 4 3 2 1, find y of n. Let us see the MATLAB code. The MATLAB function myconv2 calculates the convolution of two input sequences x and h provided with their corresponding time indices n of x and n of h. It determines the starting and ending indices for the resulting convolution by adding the respective initial and final time indices of both sequences. Then it generates the time indices for the convolution result based on the calculated range. Finally, it computes the convolution using built-in conv function in MATLAB, returning the result y along with the corresponding time indices in y. In the calling section, the MATLAB script demonstrates the convolution of an input signal x with an impulse response h using a custom function myconv2. In the first part, x is defined as 1 minus 2 3 minus 4 3 2 1 with corresponding time indices n of x ranging from 0 to 6, and h is defined as 3 2 1 minus 2 1 0 minus 4 0 3 with time indices nh ranging from 0 to 8. The custom convolution function myconv2 is then called to compute the convolution of x and h resulting in y and ny. Now by running the output, two subplots are created within a figure. The first subplot displays the convolution result y against its time indices ny using a red stem plot with a line width of 1.5, whereas in the second subplot, x is shifted by 2 units to the left. As you can see, now the x-axis indexes are starting from the value -2. The convolution result of this shifted x and h is computed again using myconv2, producing a new y and ny. This result is then plotted similarly to the first subplot but with a green stem plot. Both subplots are titled convolution result y of n and labeled with appropriate axis titles for time n and amplitude. Thank you so much for watching. See you in the next video. Allah Hafiz.